Welcome back, everybody. For the last little while, we've been studying some information about polar equations, and we've played with that. There's a lot more that we could do with polar, including some fantastic ways to solve some problems through De Moivre's theorem. But I did really look at it and try to think about what would ultimately benefit us the most in the long run. And right before school canceled, we were leading up to a process of studying law of sines and cosines. And frankly, I kind of just forgot that that's where we had been. And so we shift gears. We did a couple other things. So I think for the closeout of the year, we're going to study law of sines and law of cosines. It's actually, for most people, a little bit of an easier topic. It's a little more straightforward. It's not about unit circle. We're going to be stepping away from that. And just look at a simple application. So I want to start this first video at a short one, reminding us what the law of sines is and what we can use it to do and how we can utilize that to solve some pretty quick little problems. So let's go ahead and take a look at what the law of sines says and how that works. So here we go. So right off the bat, how the law of sines works is we start off with a triangle. Okay, so I'm going to start with a very simple little triangle, nothing fancy at all. It's clearly, decidedly not a right triangle. And just for fun, I'm going to call this side, this angle here, A, B, and C. And clearly the normal SOHCAHTOA trig is not going to be applied because I don't know whether or not this is a right triangle or not. So that's kind of a bummer. So what do we do? So the first thing that we can do is, if this angle right here is capital A, people have decided long ago that we're just going to go ahead and make a smaller case value across from big A, and then little b, and then little c would be down here. I still can't use basic trigonometry, but if we were to draw in, and I'm going to switch colors to show that this is a different story. If we drew in what's called an altitude, which is just a line that is perpendicular from a vertex to a side opposite it, sometimes this perpendicular won't even hit, because if it was an obtuse triangle, sometimes it hits outside, but you can still do that. And let's call this H. Now that we have a right triangle, what we could say is that the sine of A, and don't forget that the definition of sine, SOHCAHTOA, is opposite over hypotenuse. So in this little fictitious triangle, it's H over B. So that's what we have. So H over B. In other words, that height would be B times the sine of angle A. Now, in a similar way, if we looked at this other side and we asked what was the sine of angle B, we could similarly say that that is H over A. And if we cross multiplied, we could say that H is then A times the sine of B. But clearly, if H is equal to this and H is equal to that, well, those two things have to be equal. That's, you could call that substitution, or you could call that the transitive property of equality, is the fancy way of saying it. But I'm going to say that B times the sine of A is equal to A times the sine of B. Now, the next step is a little bit weird. You just kind of have to know where you're going, what you're trying to prove. But I'm going to go ahead and divide both of these sides by A and B at the same time. It's just kind of because I know what I'm doing here. But those two B's are going to cancel, and I'm left with what we call the law of sines, which is the sine of A divided by little a is equal to the sine of B divided by little b. And if you went ahead and rotated the diagram and you did a similar kind of a story, you could, by extension, get that the sine of C is C. I don't want to prove that right now because it'll make the video too long, but trust me, the argument is identical. These collectively are known as the law of sines. And where this is used, it's used to solve ASA triangles. Now notice, if you have ASA, that means I've given you two angles and an included side. Maybe I gave you angle A, and I gave you angle C, and I gave you the length of side B, and I asked you to find all these other pieces. But it's two angles and an included side. Well, the nice thing is if I give you two angles, then we know based on 180 degrees in a triangle, we actually have all three. AAS is another one that it works for. And how this works is, notice that I give you 3 pieces of information. So if I kind of go like this, I have this nice little ratio. And in both of these stories, effectively, you have 3 out of the 4 pieces of data. So it's going to be very, very easy to solve. Or if it was like this, I would still have 3 out of the 4. Or right here, I would have 3 out of 4. Now, as it turns out, this is the kind of the dicey one that is sitting right here. It also can be used to solve the SSA, also known as the ASS triangle. That is not what I'm going to address in this particular video. I'm going to do a separate video for that particular piece of the puzzle, but let's look at 2 examples of how to solve a triangle. And so the first one I have is, let's just say that you were given that the measure of angle A was 53 degrees, and that the measure of angle B is 41 degrees, and that C itself is somehow, say, 27 inches. Now, when I draw those things, I just come off to the side and I draw some random triangle. I don't try to make it look perfect or cute or anything, and I just label it however the heck I feel like labeling it. I usually label it the same as I did this one above, A and B at the bottom, but it could be in any order you want. Notice that I made no care. The fact that these are obtuse or acute, I don't really care at all. And I'm going to go ahead and label everything as I get it. And now C is 27 inches, which of course C is supposed to be the one that is opposite the angle C, so this is 27 inches. Now, I'm going to change colors because that's just the given information is what I did in that introductory color purple there. So what's going to happen now is I'm going to use, I just happen to know that if this is 53 and if this is 41, using 180 degrees, I could say that this is 86. So that's pretty quick. So I can add to my mix that the measure of angle C is 86 degrees. Now I'm going to go ahead and use the law of sines and see how that plays out. What I can see is that the sine of 86, and the reason I'm going with that is I always try to start with a pair that I have, which is an angle and a side that are in partnership. So the sine of 86 would be set over 27 because in the law of sines they're across from each other. In the same way that, let's say, the sine of A, which is 53 degrees, would be to its partner. Now, if I were to cross multiply, I could say that A sine of 86 would be the same as 27 inches times the sine of 53. Now, that means A is 27 inches times the sine of 53 degrees divided by the sine of 86. And that would tell me, grand total, that the measure of A would be 21.615 inches. Now, I'm not going to take the time to show all of the steps for that, but in a very, very similar way, I could do sine of 86 over 27 is equal to the sine of 41 over B. I could just replace sine of 41 and B. And if you did that process right there, you would find that B, through that similar process, is 17.757 inches. Now, I'm not going to talk too long about that, but I would like to put that in and kind of remind you of a simple fact that you learned back when you were in Math 2, a long time ago for some of you guys. But as it turns out, what we learned back in Math 2 is that in any triangle, the largest side will always be opposite the largest angle, and the smallest side will be opposite the smallest angle. So you can validate your answer pretty quickly by just thinking about whether or not that actually was in fact the case. And I did want to mention also very quickly that this problem, if you study the purple, I gave you 2 angles and an included side. So this particular story was an ASA example. Okay, we're going to do one more real quick. Of course, we're going to look at the other side of that coin, and that's going to be this guy right here. So this time, I'm going to tell you that the measure of angle B is 79 degrees. The measure of angle C is 71 degrees, and B is a 14 centimeter segment. So I am a creature of habit. I will admit that. I'm just going to go A, B, C as we've done. I'm going to label what was given, which was 79 degrees for this one, 71 degrees for that one. And side B, of course, is sitting right here. So that's going to be 14 centimeters. And that looks like two angles in a non-included side. So that looks like AAS is that given story. So what I could do is, if I have this, I could say then that the sine of 79 over 14 centimeters would be equal to, I guess I'll just go up here with the sine of 71 over side C. So just like in the previous video, previous question, excuse me, if we did C sines of 71 equals 14 times the sine of 71, so C sine 79, 14 sine 71, and we just go ahead and do a quick division. I'm going to find that the measure of C is 13.48, I think 6, can't read my notes there, centimeters. And similarly, we would be able to find that, well, you can tell that based on this right here, that the measure of angle A is 30 degrees. And if we set that one up, we're going to be able to find through exactly the same kind of ratio, just using A instead of B and C information, we would find that A is 7.13. Now, I would love to see you guys put that information on your diagram when you're all said and done, because I'd like you to think back to what I mentioned about the triangular inequality. Are these in fact in line with what we said? So notice that these two sides right here, 14 and 13 and a half, are relatively close together because these two angles are somewhat close together. And notice that the smallest angle is opposite by far the smallest side. So that's just a little bit of the application. It's just a little bit of the application of the law of sines to solve a triangle. Of course, sometimes we have great right triangles, and SOHCAHTOA is great, but the law of sines works fantastic when you do not. It actually will work on a law of sines, but if it's a right triangle, but it's kind of a waste to use the law of sines in that situation. But hopefully that's going to be helpful to you to solve a few problems. In the next video, I'm going to go over that dreaded side-side angle case, which sometimes we'll call angle side-side, just to kind of hit you that's actually something significant. So I'll see you again in a moment. You will need to watch both videos before you can do the work on this. Awesome. Thanks. Bye-bye.